Okay, so we're going to look at magnetism today. We looked at electricity. We saw how we can create circuits and push electrons around. We've all played with magnets before at some place or the other and kind of know how they behave. They're kind of cool, right? The first time you ever played with one, it must have been kind of, that way that you could move touching it. And I bet you tried um, some cool tricks and stuff on the side. Well, let's take a little deeper look and see what causes magnetism. A little fun history. Some tell us about a Greek guy named Magnets who lived in Magnesia, and I'm not really sure who they named it after, but he'd have nails stuck to his shoes, um, and the metal tip of his staff got stuck to the large rocks, and and his shoes would get stuck to the rock, and he's like, "What's going on? Why is it sticking to me?" And so it was magnetism on those rocks. What kind of materials usually have magnetism? Well, there's iron, cobalt, nickel. They're the most common ones. They are easily magnetized, and it's got a lot to do with the, the available electrons they have and what shells they're on. Going down below, um, they saw that these stones would kind of line up and point towards, or some a part of it point towards the North Pole, and so they used to call that part that pointed towards the North Pole, and we'll come back to that on how that kind of changes the way we do things. So anyway, they'd use these stone slivers that would find themselves aligned to a certain way, and they use them to make streets that would be going northwest or east, north south or east west. Magnets come in various forms, but here's a really interesting thing about a magnet. Like a charge could be either positive or negative. A magnet has both poles in one space. So you have it's like having your positive charge here and your negative charge there. It's kind of like that kind of system. And so every magnet has a north pole and a south pole, and the field lines, which we'll see later, come out of the North Pole and kind of make their way into the South Pole. So we look and see how the field lines pop out of the North Pole and go into the South Pole. These are like these fictitious lines that we create to kind of emulate the field that's around here that something will react to. So you're kind of played around with magnets and seen how if you would brought this North Pole near another North Pole, it would push it, but if you brought it near the South Pole, it would pull it. And sometimes something's going to spin around because they want to get to the right side. Now, here's an interesting thing. So, well, what if this is the North and there's a South? Why don't I just break this down the middle? And when I have a North and a South, then, well, here's what happens. When you break this down in the middle, you end up getting another set of two little magnets, each one having a North Pole and a South Pole. And you could continue to do this forever until you come down to the final molecule that's creating that North Pole, South Pole. And then we'll see in a little bit what really causes magnetism. And you start to realize that, this is just the way it is. You can't just have a North Pole or just a South Pole. And so that's what's being stated here. No monopoles allowed. Okay, so you north and a south, but can't have just a north or just a south. Okay, even if it's an oddly shaped magnet, it still has a north pole and a south pole, as we see over here in a horseshoe magnet, and we see how the field lines are coming out of the north and into the south. And again, we know that poles that are the same are repelled, and they're the same that are different repel each other,